Hello everybody, welcome back to this lecture. We were discussing about top-down parsing and we saw that there are two types of top-down parsing. One is without backtracking and the other is backtracking. So for backtracking as well as without backtracking, this particular function this particular type of parsing called recursive descent parsing is useful. So let's see what this algorithm is like. Before I come to the algorithm, let me talk about something about this. So, when we talked about backtracking, I gave the example of a person waiting at a junction and trying to find the house of your friend. So, in backtracking, the person will go to each and every lane and try to find out and come back to the junction in case he or she doesn't find out. Now, in case of predictive parsing, now along with the friend's house, say a flag will be say the friend says that I'm going to put up a flag on top of my house. So when this person sees the flag, then by looking at that, the person can directly go to the lane where the friend's house is. So that flag is the look ahead. So these two types of parsing algorithms, that is with backtracking or without backtracking. There is one particular algorithm which can work for both, and that is your recursive descent parsing. So you can have recursive descent parsing with backtracking and you can have recursive descent parsing without backtracking. Okay, so if we look at our algorithm, this is our algorithm. If you see this, now recursive descent parsing can be implemented as you can consider each of the non-terminal to be something like a procedure. So if I have a production like this, A derives x1, x2, something like this, okay, then for every non-terminal I will have one procedure, one function. So A here, so I may have for A I may have a function like this. So void A is calling, so this is the body of the function A. So what is there? In the first statement I have choose a production A derives x1, x2, xn. Okay, so there may be multiple A productions, x1, x2, x up to xn. Okay, so I may have something like this: A derives x1, x2, or x3, x4. So I will choose one of the production. So suppose I choose this. Then for I going from 1 to n, okay, now here n is 2, x1, x2. So I is 2. So if xi is a non-terminal, now if xi is a non-terminal, then what we will do? We will call xi. So xi is a non-terminal, so I'll call the procedure related to xi. If xi is not a non-terminal, then it must be a terminal. If it is a terminal, then what we will do? If xi, will try to match. If xi is equal to the next input symbol, okay, then what we will do? Then we find the match, and then we will advance we'll try to read in the next input symbol. We'll advance the next input pointer. Okay, so either it is a here, if it matches here, then it is a non-terminal. So we are calling the procedure corresponding to that non-terminal. Otherwise, we are trying to match if it is a terminal. Okay, now if it is neither a terminal nor a non-terminal, then what? Then it is a error. Then it is an error. That means I have tried to match. I did not get a terminal, nor did I get a non-terminal. So this means that it is an error. So in that case, I have to come out and exit and say that the parsing is not possible. Okay. in case of when we are talking about recursive descent parsing with backtracking, then this error is not absolute. This is not absolute. This means that in case I don't find a match, it is neither a terminal or non-terminal, then I'm going to try out a different production. So what I'll do, I'll come back to number 1 and I'm going to try with another production of A. I'm going to try with, say, A derives x3, x4. And I'll continue this procedure. And how long I'll continue? I'll continue as long as I get A productions. If after exhausting all A productions, if I don't find the match, then that is an error in the parsing. So this is your with backtracking. And without backtracking, the algorithm that I have given here, this is without backtracking. That means I'm sure when I'm picking a production, when I'm picking this production, then I'm sure that this is the correct production. So I will either find a match, that is either xi will be, I will find a match, or it will be a terminal. Okay, if neither, then I will get an error. Okay, so this is your recursive descent parsing. And why it is called recursive? Because as you can see, this is a recursion. So A calls xi calls something else. Okay, so there is a kind of a recursion. Okay, and here one point to be noted is that in recursive descent parsing, if you have productions like this, A is equal to A, B, something like this, that means you have left recursion. If you have left recursion, then this will go into an infinite loop. This will go into an infinite loop. So you have to remove left recursion before you can run a recursive function or a recursive parsing procedure to it. Okay. So if I have, let's say I have, let's say I have this. This is my grammar. S derives CAD, and A is what? A is either AB or simple grammar or A. My input string is CAD. So first I'm going to start with the start symbol, since I'm going to call the start symbol. Okay, so S is called, so I'm going to expand S. So S means C, A and D. So here first I'm going to find a match to C, then I'm going to get A, so A has to be expanded. Now A, how I'll expand? I will try by expanding by AB. Now I find that there is no match here, so what do? We come back. So if it is a backtracking recursive descent, then I come back and I try out another production for A. So I'll try out the next production for A. So I try this. Now this is a match, then I try the last one. So this is a match. So I get a match here. So if it was non-backtracking, then I would not have applied this production. I would not have applied the production A, B. I would have only given this production. So this is your recursive descent. So if I have something like let's say I have a production like this is or ID. Okay, so how will I write? I'll write a function for F. So here I may have a switch because I have an option. So switch what? Token. So if the token is, say, case, if the token is open parenthesis, then what I'm going to do? I'm going to call a method called match parenthesis. Then I'm going to call E. Then I'm going to call match closing parenthesis for this production. Okay. The second option could be I may not get a parenthesis, I may get an ID. So if I get an ID, in that case what? I'm going to match the ID. I'm going to match this ID. Okay. If neither, that is default, then I will get some error case, or I'm going to call a method for error. I'm going to call some function for error. Okay, this is our switch, this is our close. So for every production, now I have to write procedures of this manner. And what this match is going to do? This match is simply going to find out what is the, maybe something like this. So match takes a character, say C. So if the C is equal to the token, then what? Then it is a match, so I'll get the next token. So token is, I will use, say, get char. I'll read the next token. Else, if it does not match, then it's an error. So this is your match. So if I find the match, then I will I'll read in the next character or the next token. If not, if it is not a match, then it's an error. So this is, in this manner you can write your recursive descent parsers. Now recursive descent parsers are easy to write by hand. That means if you are given some grammar rules, you can easily write a C program, or in any programming language, you can write a program to implement a parser. But there are more complicated grammars for which writing by hand is not possible. So in that case, you need automated systems or automated constructors of compilers or parsers. So we'll see in our next few videos how we can use these. Okay. So that is all about your recursive descent parsing.